The OREOS project envisions an end-to-end architecture to move forward to ultra-reliable and low-latency solutions. Capgemini, the University of Coimbra, and the Pedro Nunes Institute are working together to achieve this objective. 5G will enable not only better smartphones but also empower a communication infrastructure with higher data rates, lower latency, and better reliability. 5G and 6G are the future of communications and are paving the way for a new range of applications. Think in the automotive industry, where the support of low-latency communication infrastructure exists to monitor and exchange information between the robots. In the supply chain of intelligent cars. Later, these same smart cars will be part of a more complex and dense environment, like a smart city where a plethora of devices are communicated with each other. The Orchestration and Resource Optimization for Reliable and Low-Latency Services project is focused on building an end-to-end communication architecture to support these scenarios. The consortium of this project is built by Capgemini, with expertise in mobile communications and critical services, the University of Coimbra, with expertise in optimization and resource allocation in the cloud-to-edge continuum, and the Pedro Nunes Institute, with expertise in complex platforms and cloud services. One of the essential tasks of OREOS is to focus on network orchestration, which refers to actions a network controller performs in setting up devices, applications, and services in the network to achieve certain objectives. It is much like an orchestra conductor's role in directing individual musicians as they perform a piece of music together. Autonomous driving and pedestrian safety is one of the use cases considered in OREOS. The end-to-end architecture designed and instantiated allows fulfilling applications and users' requirements. Along the cloud-to-edge continuum, the OREOS architecture is comprised of 5 components. First, the radio access network. Second, the core. Third, multi-access edge computing. Fourth, service management and orchestration. And 5, monitoring, which envisions an end-to-end solution in a virtualized environment. The RAN is composed of 2 modules. First, as a southbound interface, emulators and simulators developed by the Open Air Interface Alliance are used for user equipment and G-Node B. As a northbound interface, FlexRIC provides intelligence to the RAN, where the radio management algorithms are implemented. In the core component, Open5GS is instantiated, while in the MET component, Ensconce is utilized. The service management and orchestration component is implemented with ONAP. Since there is no native communication between FlexRIC and ONAP, a REST API has been developed to ensure connectivity and policy enforcement between FlexRIC and the orchestrator. To retrieve and analyze network metrics, Prometheus is used jointly with Grafana. The REST API developed was created to establish the connection between ONAP and FlexRIC via the A1 interface, since there is no native connection between both components. Therefore, we manage the interaction between these components for policy enforcement by using Capgemini's A1 adapter. Given this architecture, and according to the gathered traffic from an XApp, it is possible to improve the bandwidth usage and allocate the requested resources in near real-time RIC. The service management orchestrator must know the type of policies and the schema related to policies to create an XApp that will consume them on the RIC. Here we have 4 terminals, a 1 interface terminal, G-Node B, near real-time RIC, and XApp. We will send messages regarding a slice creation from the A1 interface to an XApp. First, we initialize our near real-time RIC to further connect to our G-Node B. After doing this, we have created an association between our near real-time RIC and an XApp responsible for handling the RAN functions. At this point, we can confirm via the A1 interface that no policies are defined in our near real-time RIC. Therefore, we will add the first one with ID slicing to our near real-time RIC. This policy creation command is sent alongside its radio settings via the A1 interface to the XApp responsible for handling the RAN functions. In turn, near real-time RIC will also receive the request for slice creation. Suddenly, we can confirm via the A1 interface that the policy is configured on your real-time RIC with the corresponding ID. In the same way, we create slices. We can also delete them by making a delete request via the A1 interface and confirming the request reception on the XApp and near real-time RIC.